Okay, what we now want to do is show you why we actually had to have new notation for the parametric equations instead of just the usual ones. So the first thing I want to do is just look geometrically at what's going to happen when we start calculating the derivative. Now remember, the definition of derivative looks like the limit as delta t goes to 0. In this case, this is going to be r vector t plus delta t minus r of t over delta t. And we're going to draw a similar picture to the one we actually drew in Calc 1 when we took the derivative of sine. So what we have is we have some sort of graph that's going like this. There's a direction along the graph, because that's what the parametric equations give us. We're picking a point, and we're drawing r of t. Remember, r of t is just the vector that starts at the origin and points to where the particle is at that time. So that's r of t. Now what is r of t plus delta t? Well, that says let a little bit of time go by and then find the new location. Well, since the direction is from right to left at the moment, right? R of t plus delta t is just going to be a little bit further along the graph, like that. And that is r of t plus delta t, like that. Now, how does vector addition work? Yes, it tells us that this vector, yes, plus this vector, that little one along the graph, is equal to the new one. That tells us if we take the big one and subtract the little one, what we're going to get is this little tiny vector along the graph. Now that is what the top of this is, and you can see that if delta t is really small, these two vectors are very similar. The graph is very flat, and what you're actually going to get is a vector that's tangent to the graph. When I divide by delta t, I'm getting a longer vector than that, and if the limit exists, I'm not getting a vector of infinite length. What I'm getting is just a vector that's tangent to the graph that points in the direction of the graph and has finite length. So that's going to be part of the interpretation we have of this vector is those two things. It's tangent to the graph, and it points in the direction of the motion. And what we're going to do next is we're just going to calculate for two variables. It's no different really for three, this whole formula. And it's not as bad as you might think. So here we go. I'm going to write down equals limit delta t goes to 0. Now what is r of t plus delta t? I go way over to here, and wherever I see a t, I put a t plus delta t. So this is going to be f of t plus delta t I plus g of t plus delta tj. Now that's r of t plus delta t. That's the new vector we got. The first vector is just going to be f of t I plus g of t j all over delta t. And what we're going to do is combine like terms. Now what do I mean by like terms? I'm going to combine the two things that have i's and the two things that have j's. So I'm going to say the limit as delta t goes to 0, and let's pull out the things that have i's. So I have f of t plus delta t minus f of t all over delta t, and there's an I right here, and then plus the limit delta t goes to 0, and combine the things that have j's. So I'm going to write down g of t plus delta t minus g of t all over delta t j. Now, when we write down parametric equations, remember f of t is a function of a single variable. And when I take a function of a single variable and do that with it, that's just the definition of derivative, right? So that is just going to be f prime of t. The I doesn't even come into the calculation. It just sits there the whole time. And so I get f prime of t I. Same thing here. When I look at that thing right there, the j doesn't actually come into the calculation. There's no t's in the j. What I'm going to get is g prime of t j. If there were three variables and there happened to be a k, it would just be it again. Now what does this mean? Let's write this down as a conclusion. To find, algebraically, r prime of t, just take the derivative of each component. Now I think if we had just been asked for the derivative, we'd have tried that anyways, but it wouldn't have any interpretation. There would be no good reason we could use to justify why that actually is finding what we want to be, the velocity. Okay, so when we look at the derivative, we know that it's tangent to the graph. We know it's pointing exactly in the direction of motion. When we take the derivative, we're just going to take the derivative of each component, which is nice. I want to talk about the units. So I'm going to bring back the picture, and let's just talk about the units over here. Normally, since we're talking about motion, the units of t is usually time, so I'm just going to put t in seconds. Any unit of time is fine, but I just want something to sample so we can actually point to. F of t and g of t are usually distances. They're parts of lengths of vector. So I'm going to say the units of f and g are something like feet. They could be any unit of distance that you want. Meanwhile, let's go back to our picture. Our picture looked like this. We had a vector that looked like this, and it was tangent to the graph like this. I want to know how long this vector is. How long is r prime of t? Well, it is a vector. We know how to find lengths of vectors. It's going to be square root of here. It's going to be f prime of t quantity squared plus g prime of t quantity squared. If there was a k, we'd just have another plus h prime of t quantity squared. But I want to look at the units. Remember, the units of f prime are feet. In fact, it is feet over seconds, right? So what I actually get on the inside, right, is feet over second squared plus feet over second squared, and I can actually pull out feet over seconds out of the square root. So the units of the length of that vector are in feet per second. In other words, it should tell me if that point were to fly off the graph, right? It's pointing me to exactly where that point would land in feet 1 second later. That's exactly why we call it speed. It's got the right units. It's exactly telling me what I think it should tell me. It's just going how far that thing would actually travel in 1 second if it were to fly off the graph. So the definition of speed is just going to be the length of the derivative of our vector. So finally, what do we have here? We have a vector that is tangent to the graph. It points in the direction of the graph. Its length is actually the speed, and that's why we call the derivative of our r function the velocity vector. For those three reasons. And by the way, it's easy to take if someone actually gives us a formula, because you can just take the derivative of each component.